To demonstrate the utility of the supermagic formula, we're going to turn back to our tried and true example of the spider on a DJ Roomba. So here we have our Roomba robot. We're going to put the center of the robot at right here in point R. And then we have the spider located at point P. And this spider can travel along this line in and out towards and away from the center of the robot. And then we want to find the acceleration of that point P in our frame A as drawn here. The position of point P is defined by this vector ROP. And it is the sum of the following two vectors, R, O, R, plus this vector here, R, RP. So just to label that again, this is R, RP, this is R, OR. Now to use the super magic formula, we have to define one of these vectors, so this one here in frame A, and then this vector here, RP, in frame B. And so we've done this before, so we're going to write ROR is equal to some magnitude in the A1 direction plus some magnitude in the A2 direction. And RP is equal to, well, first we have to define our reference frame B. Again, it makes sense to put it here, orient it like this, where this is B1, this is B2, and we'll call the length at which the spider is with respect to this center point R, we'll call that L. So we can write that RP is LB1. So now we've met our requirements for writing the position vector in order to use the super magic formula. All right, now that I've cleared some space, I'm going to go ahead and write out the super magic formula, and then we're going to go term by term, and I'll show you how to calculate them and go over again what each term actually means. So bear with me, I'm going to write this out hopefully correctly, and I'm going to try and do it quickly. Okay, so there you have it. This is a super magic formula, and it will give you the acceleration of point P in frame A when you have a position vector. And so just to write this out again, when you have a position vector, that can be written as the sum of two vectors here, where one vector is written with respect to frame A, sorry, and then you have a second vector that's written with respect to frame B. So let's start with this acceleration term here. So it's asking for the acceleration of point R in frame A. So that, if we want to define the position of point R, that's in frame A, that's this position vector right here, ROR. So to take the acceleration, we're just taking the double derivative with respect to time of this position vector here. So that's easy enough. That's x double dot A1 plus y double dot A2. Next on the list is this term here, which is the acceleration of point P in frame B. So again, if you look at our position vector of RP, you see that is the position of P in frame B. And so to get the acceleration, again, we just take the double derivative with respect to time, which again is easy enough. We just have L double dot B1. Again, the spider can move, so that's why that length L changes. Now we have this term here. So we have 2, of course, and our angular velocity, should remember, I'll just write it here just in case, our angular velocity of frame B in frame A is theta dot B3. So here we can write 2 theta dot B3, and this is crossed with the velocity of point P in frame B. So again, if you come back to this position vector of RP, so that's position of P in frame B. So now to get the velocity, we just take the first derivative of this. So that's simply L dot B1. Okay, now we have this term here. So the angular acceleration, so this alpha here, angular acceleration of frame B and frame A is simply the derivative of angular velocity. So if you take the derivative with respect to time of this angular velocity vector, you get theta double dot B3. And our position vector RP is simply L B1. And lastly, we have our longest term, right? But probably the easiest to write out. So again, our angular velocity is given here. So that's just theta dot B3. And then we write that again, theta dot B3 crossed with our position vector, which is L B1. Just make sure that this looks more like a cross than a plus sign. Okay, so this is the unsimplified version. Hopefully I didn't obscure anything there. There we go. Of our acceleration of point P in frame A. So, I mean, you can see that the supermagic formula, while it's long, once you have it, if you have it written down, finding each of these terms, for most examples, is actually quite easy, and it can be a much easier process than going through and deriving everything. So now we just have to go through and simplify some terms here. So let's do that now and get to our final equation. So again, our acceleration of point P in frame A is equal to x double dot A1 plus y double dot A2 plus L double dot B1 plus, and here we have 2 theta dot, and then we have 2 L dot theta dot. And then we have a cross product between B3 and B1, which is going to give us B2. Then we have plus theta double dot L. So I'm just going to write L theta double dot. And again, we have this cross product between B3 and B1. So that's going to give us B2. And now we'll still leave this for now. It'll take us one more step, but we're going to have theta dot B3 crossed with, and now we take the cross product of this inner term, which is L theta dot B2. And then we have just one more simplification. So I'm just going to quickly write this all out again. And so here we have that cross product. So we have L theta dot squared, and the cross product between B3 and B2 is actually negative B1. So we're going to make this a negative sign B1. You can also, I guess you can go a step further. You can group terms if you'd like. So again, so for our B1, we have L minus L theta dot squared B1 plus L2 L dot theta dot L theta double dot B2. And so this is the acceleration. And again, if you check this with the prior approach that we used, you should arrive at the exact same answer, right? So the answers are similar, identical, right? And that's because, and I've mentioned this before, that doesn't matter what approach that you're using to calculate, whether it's the velocity or the acceleration. The method can change, but the answer must always be the same. And so there you have it. That's how you can use the super magic formula in our spider on a Roomba example. And so we'll go through another example where we're using two moving reference frames. So you have frame B and frame C. So you get a additional example on the utility of this super magic formula.